All right, so for the last problem this week, we're going to perform a basic analysis using a Gibbs reactor. And so a Gibbs reactor is one of the types of reactors we can model in CHEMCAD, where basically we just need to specify what's going into the reactor. And then in our component list, we need to have a list of all possible products, so all possible components in our system. And the Gibbs reactor will work such that given that feed stream, it'll determine right what your products are or what the product is to minimize the Gibbs free energy of my system. So based on what's going in, it'll try and determine the composition of my product stream so that it minimizes the Gibbs free energy of my system, right? Which is why it's a Gibbs reactor. So it's nice in that I don't need to define the stoichiometry, so I don't need to define my reactions whatsoever. All I need to be able to define is, well, I need to specify what's going into the reactor, which I should know, and then my component list makes sure I have all possible products that could form, and then it'll take care of the rest. And so we'll use a Gibbs reactor to model a flare, right? Because for our design project, for the second design scenario, you're going to flare you're going to be flaring natural gas, and then natural gas with some ammonia and potentially H2S in it. And so we just want to look at setting up our Gibbs reactor. We'll look at the case of combusting natural gas, which will model as methane with air. And then we'll look at when we have small amounts of NH3 and H2S in it, what happens. And these are just interesting problems because we'll see NH3, we end up forming diatomic nitrogen, right? So not even knowing what the relevant combustion reaction is for NH3, the Gibbs reactor will give us the correct product distribution. Okay. So anyways, so the scenario is I'm going to start out, I have a new flow sheet. So I'm going to choose my engineering units. I'm going to make a common SI, but change my mass to kilomoles. And then in terms of components, okay, so we're going to combust natural gas, which will model as pure methane with excess air, right? And so now we can't use in our component list, we're not going to select air, right? So we can select air when we have a process not involving a chemical reaction, right? So when air is, say, a carrier gas. So now when I want to, combust methane, right, with air, I'm going to need to model air in its atomic form. And so I'm going to take it to be a mixture of nitrogen and oxygen, 78% nitrogen and 22% oxygen. All right, so I actually need to be able to define the chemical makeup of air so that I can appropriately model that chemical reaction. Okay. So thinking about my Gibbs reactor, right, so I'm going to need to add natural gas, which I'm going to take to be methane. Then air, I'm going to model as, I'm going to use O2, right, oxygen. And diatomic nitrogen, N2. And then I need to be able to add all possible products, right? So I don't need to know exactly what the reactions are, but I need to, come up with, a list of all possible products. And so, this is when I combust ammonia, right? I can start listing everything that comes to mind, and I can always narrow the list down based on the distribution that I see. Okay. But I know for basic combustion reaction, I'm going to expect some carbon dioxide, CO2. I'm going to expect some water. And actually, just because, okay, I have CO2, let me just specify CO, carbon monoxide, and let's see what we get out of our simulation as well. Okay, so I expect my standard combustion reaction to be CO2 and water, but let's throw CO in there as well and see what happens. Okay, so I'm going to click OK. Okay. I'll recommend our thermal model, and that is all good. Okay, so in my Gibbs reactor, so you can narrow down to reactors. Okay, but I'm going to drag my Gibbs reactor in here. Okay, and into my Gibbs reactor, what I'm going to do is, since I have natural gas and air, I just said 100 kilomoles per hour of natural gas in excess of air, is I can have any number of connections here in terms of input streams. Okay. But what I'm actually going to do is I'm going to send my gas and air into a mixer, which I'll then send to my reactor. Okay. I tend to like a mixer because then I could double click on the product or the stream exiting the mixer and know exactly what's going in. Okay, and I'll show you what I mean. Okay, so there's my mixer, and I can actually rotate it if I want to. Let me rotate clockwise, so the red, right, this is going to become my input to my reactor. And let me do two feeds. One's going to be my natural gas, and the other will be air. Okay, and we're going to have 100 kilomoles per hour of natural gas at 20 degrees C in 1 bar. Okay, so connect that. We'll connect this, and I'm going to put one product stream down here. Okay, so stream 3, I'm going to call that air in. Okay, now the temperature in that really doesn't matter. This is just for illustrative purposes. So I'm going to take my air to be at 20 degrees C in 1 bar. Okay, I'm going to specify its composition. So we said we'll take it to be 78% oxygen, or nitrogen, and 22% oxygen. You could always change this if you want. And excess, it's going to make it 500, and we could always tune it down if we wanted to. So I'm going to throw in a ton of air. Okay. Then I'm going to have, so this is going to be my natural gas. Okay. So I have a natural gas stream also at 20 degrees C in 1 bar. I'm going to specify mole frac and say this is pure methane. And we'll get a flow rate of 100 kilomoles per hour. Okay. So I could have taken these two streams. Come on, don't know why the label's not appearing. Okay. So I could have taken these two streams and sent them directly in to my Gibbs reactor, and that would have been fine. Okay. But the benefit of using the mixer, right, is if I double click on the mixer, okay, the only thing I need to specify is, the outlet pressure if I want the pressure to change. And so, right, I'm just going to, specify that it's 1 bar. The two inlets are 1 bar. So the only benefit of having a mixer is if I run selected, if I just run the mixer, okay, then I can look at the exact makeup of the stream that's being fed into my reactor. If I fed my air and natural gas, okay, if I fed those separately into my reactor, well then, if I wanted to know, say the mole frac composition of what's going in, all right, so molar flow rate's fine, but if I want to do the mole frac composition, well then I'd actually have to figure that out by myself, okay? But, since I've mixed them, right, the mixer will determine it for us, okay? Cool, right? And so I've got pretty close to the same mole frac of methane and oxygen, all right, which is cool. Okay, so only benefit of the mixer is being able to look at that composition of that stream, that feed stream, then to my reactor. So now when I double click on my reactor, okay, the operating mode that I'm going to use, right, ultimately this is going to be a flare. And so I'm going to make it run, I'm going to have it run adiabatically, so I'm not going to add heat or remove heat. And what I'm going to expect out is some product stream, and it's going to be at some super high temperature, right? There's my flame coming out of my flare, which I can then use to say generate steam. So take some cooling water, heat it to generate steam, which I could then use elsewhere in my plant. Okay. So I'm going to have it operate adiabatically. Okay, it's going to be a vapor phase reaction. Okay, you can specify a pressure drop or anything like that if you wanted to. Okay, and so yeah, that's all, right? It's being operated adiabatically, and then I don't need to specify anything else, at this point for this problem, unless I wanted to. Okay, you can click, I should add, you can click inerts. So if there's a component that you don't want to participate in your reaction, right, then you could select it from the inerts. Okay, but I click OK. Okay, it's going to show us the chemical breakdown. So let me come back. It's going to show us the chemical breakdown, right, of the species, right? Because essentially, it's just going to, based on, right, what's going in, it's going to, break those molecules apart, right, and determine, right, the ultimate composition and distribution of that product stream. Okay. So I'm going to click OK, and then I could do a run selected or run all, but if I do a run selected, okay, it runs. Now I'm going to look at my product stream, right, it says some super high temperature, right, this is a combustion reaction, and we see that, well, I still have some methane left, okay, so I still have some methane left. I've consumed all my oxygen, so this tells me I need more oxygen, right, I don't have enough air, right, I'm consuming all my oxygen, right, and I still have some methane left. Okay, so I have my nitrogen, which should be unreacted. I form a ton of water. This is actually suggesting that I'm forming a bunch of carbon monoxide, and then I have my carbon dioxide as well. Okay, cool. So what I'm going to do is first I'm going to start with my airstream. Okay, oh yeah, I need to crank up. I need more oxygen. So let's make that 700 kilomoles per hour. Okay. Let's do a run all. And so coming out now, pretty much all of my oxygen is consumed, as is all of my methane. Okay. Excellent. So oddly though, we're still forming more carbon monoxide than carbon dioxide, so which would suggest an incomplete combustion. So what I'm going to do is I could try and do it two ways. I could make CO an inert, or what I'm going to do here is I'm going to remove carbon monoxide, right? Just because I don't expect that to be the case, right? As long as this is burning cleanly, right, it's CO2 that I should form. So once I eliminate carbon monoxide as a potential product stream, well then it's no longer an option. So I'm not generating any carbon monoxide, but instead I'm generating all CO2. Okay, and so now I see all my oxygen again is consumed. Okay, again my major product now is CO2, not CO, and so I find in making CO2 I'm consuming all my oxygen, but I still have unconsumed methane. Okay, so I'm going to have to increase the flow rate of air some more. So let's make this 800, flash it and run all. Now all my oxygen's consumed, still a little methane. Wasn't enough. Run all. Okay, so now I still have a tiny bit of methane left. Come on. So make that 1,000 kilomoles per hour of air. 1,000 kilomoles per hour of air. Now I've consumed all of my methane, right? I have some slight amount of oxygen left. All my nitrogen's left and uncombusted. And then I'm forming, carbon dioxide and water, right? A 2-to-1 stoichiometric ratio. Okay, so combustion process, right? My reaction goes to completion. I generate a bunch of water and carbon dioxide, and I have this exit temperature at this, high extreme temperature. Okay, if I were to look at my reactor, it'll give me the overall heat of reaction, okay, which is cool. Okay. But really what I could use is I could take this stream, I could send it to heat exchanger, in which I cross with cooling water, and I could come up with an estimate of, the rate at which I can generate steam, which could be used elsewhere in my process, my plant. Okay. And we can play with that in the second if you want. Okay. Now in the second part, it says, well, what happens when NH3 is present, and then what happens when you have NH3 present, then H2S. Okay. So what I'm going to do is in my component list, I'm going to start by adding ammonia, NH3. Okay. And then I'm going to imagine adding, so I'm going to diatomic nitrogen's already there, N2. I'm going to look at maybe adding NO2, right, nitrogen dioxide. Okay. So I added water, nitrogen dioxide, N2 is already there. And then for my natural gas, I'll make it so it's 0.99 mole fracs methane, but then let's put a little ammonia in there, so 0.01 mole frac ammonia. So when I do that and run, okay, I still have my high temperature. All my methane's consumed. I have an excess amount of oxygen. My ammonia is all consumed, right? The kilomoles per hour of ammonia is 1 times 10 to the negative 6. And what I see is I'm primarily forming nitrogen, and then I'm making just a small amount of nitrogen dioxide. Okay, but it looks like primarily when I'm combusting ammonia, the primary product is nitrogen. Okay, so remember when I click on this, if I look at this in kilomoles per hour, okay, we have 780 kilomoles per hour. Actually, maybe I should make it a little bigger, right? Because I'm making 0.5 kilomoles per hour of additional diatomic nitrogen by combusting our ammonia, and then some 0.002 kilomoles per hour of nitrogen dioxide. Right. So the primarily effect is I'm making diatomic nitrogen. I said what happens when I add H2S. So if I want to add H2S to the mix, okay, hydrogen sulfide, and then I can say, well, maybe it's SO2 that I'm going to form, sulfur dioxide. So if I add SO2, if I want to add elemental sulfur, just like I just had, so similar to what I had for the case of nitrogen, to my natural gas stream. So let's make it so we have a little more ammonia and H2S to be able to see anything. So we make this 0.8. Okay. And so if I do a run all, so now I have a 1/10 of a mole frac of ammonia and H2S going in. Okay. It looks like, so again, my ammonia, right, I'm consuming it, and it's primarily forming nitrogen, diatomic nitrogen, and then some small amounts of nitrogen dioxide. Okay, so looking at my inlet stream, this was 780 kilomoles per hour of nitrogen. So I'm making, say, 5 kilomoles per hour of additional diatomic nitrogen, and then just some small amount of NO2. Right, so combusting NH3 primarily forms diatomic nitrogen. I could probably even eliminate the nitrogen dioxide for my simulation. When I combust my H2S, right, my H2S is completely consumed. I'm not making any sulfur, right? It's being converted to SO2. Okay, so combusting my H2S forms SO2, and then in terms of combusting my ammonia, right, it looks like it primarily forms diatomic nitrogen. All right, and so then my last comment is, okay, I have this stream now, which is really, really hot. Right? How can I think about recovering that heat to use elsewhere in my process? Okay, well, I could send it to a heat exchanger. Okay, well, if I send it to a heat exchanger, boom. Okay, in the first operation, I could say, hey, what if I have a pressure drop of 0 bars? But what if I say I want that exit temperature to be, let's go crazy, 30 degrees C. All right, so if that, I'll do a run selected. So if I wanted this temperature to decrease to 30 degrees C, all right, I could calculate the heat duty. That's the amount of heat that would need to be removed from that stream. All right, like 78,000 megajoules. If I want to think of that in terms of steam, steam generation, let's see. And hey, you could always add a controller to optimize this animal. Okay, but stream 6, I can make, say, pure water. Okay, and let me say I have, I start crazy, 500 kilomoles per hour at a temperature of 20 degrees C and 1 bar. Okay, so now when I run this, right, I'll still specify the exit temperature, okay, of stream 5. Okay, So now if I run this, ah, so it didn't like that. So let me, so that, oh, I think the problem is I specified that's 20 degrees C. That temperature going in is 20, well, no, I specified it to be 30 degrees C, right? So hold on, let me make sure I've got it specified correctly. Stream 5, right? Stream 5, I want to be at 30 degrees C. Right, so it might not, it might be that it's not possible. So let me take stream 7 instead. So that's my cooling water. And let's just, what happens if that increases to 60 degrees C? Okay, so we're going to take it in terms of baby steps. Okay, so what I specified is I have cooling water, 500 kilomoles per hour, 20 degrees C. Okay, and I want to set that temperature to be 60 degrees C. Well, then, I still have an insane, temperature. So before, when I was specifying a flue gas of 30 degrees C, it's just saying, hey man, that's not possible, right? You're not giving me enough water. So yeah, so if I want to specify this to be, say, 101 degrees C, so I get some superheated vapor coming out of it. All right, so I've got, this is 101 degrees C. It's at 1 bar superheated, and then I still have, heat to spare. If I were to make this 1000 kilomoles per hour, okay, and again, I could just run selected since this is unchanged, right? I can generate 1000 kilomoles per hour of superheated steam, right? And I still have heat to spare. Okay, so this is, kind of the game I could play around with. You could perform a sensitivity study, or use a controller to try and, solve for, trying to come up with an, right, so that's too much. So trying to come up with an estimate of how much steam I can generate. And if you look back at, say, your Giancopoulos book for mass transfer, you can try and get an estimate of, what temperature you might expect for your, what temperature you might desire for your steam, and so on. Right, so 3000 too much, 2000. Man, hold on, 1000 worked. But bam, okay, so 1500 works. All right, and still, right, my exit still, my gas is, almost 100 degrees C. Okay, so cool, right? And so this would just be then heat, right, in the form of steam, right, that I could use elsewhere in my plant. So send that to heat exchanger where I need to heat some inlet liquid up to higher temperature. And then, hey, maybe even if you're using that elsewhere, maybe I'm using it to preheat my, let's see, so that's my natural gas. So maybe it's, so we have our stripping column, right? So maybe it's, I would use this to, preheat my water going into my plant, right? But again, I'm just looking at, so remember in our project, in case you're watching this from elsewhere, we're using natural gas to strip ammonia from water, right? And the water contains ammonia, it's sour water, contains a little H2S. We're going to use natural gas as our stripping gas. So coming out the top, we're going to have natural gas plus some ammonia plus some H2S, which we're then going to send to a flare, right? So we're just modeling that flare process. But one thing you could do is, now that I have this heat that's being generated, I could recycle that back and use it to preheat my liquid stream going in, right? Preheat my liquid going into my stripper to try and drive off more of that ammonia and H2S. Okay. But this is just that flare. Okay. Hope that helps. We'll play around with this more in class.